Unmuted?
Yes, he has joined. And Dr. Divya, the introductory slide, please.
Yes, ma'am. Yes.
No. Just please ensure that he is logged in, and I don't know, matlab, I saw his name, but
Yes, he is the co-host now. Dr.
okay.
Saurav, next slide now. So welcome everybody. Next session of electromagnetic theory. Today our is the first day of electromagnetic theory of the master's level being delivered by Dr. Saurav Soor from the Department of Physics and Astrophysics, University of Delhi. And I request Dr. Pushpa Bindal to introduce the speaker.
Yeah, sure.
Welcome, Dr. Soor. Welcome.
Welcome, Dr. Saurav. Uh, Okay, so participants, we have already had a formal beginning of the session and we have already had first talk of the day. Now it is time for us to listen to our second speaker, Dr. Saurav. So it is, a great pleasure for me to introduce Dr. Saurav to the participants. So Dr. Saurav did his PhD in 2005 on the thesis entitled Cosmic Phenomena in String-Inspired Space-Times with Torsion from Jadavpur University, Kolkata, India. He had worked as a postdoctoral research associate at Institute of Physics, Bhubaneswar, India, and University of Lethbridge, Alberta, Canada, Saha Institute of Nuclear Physics, Kolkata, India, before joining as a regular faculty member at the Delhi University. He had taught many core special theory and lab courses in the curriculum of the master's degree program at the Department of Physics and Astrophysics, University of Delhi. His main research area include classical and quantum gravity, cosmology, quantum entanglement and black holes, astrophysical and cosmological aspects of string. He has more than 25 research papers and has guided many PhD students so far. His name is included in the reviewer panel of several research journals of international repute and have received recently an Outstanding Reviewer Award 2019 from the Journal of Classical and Quantum Gravity, Institute of Physics, Publishing, Bristol, UK. So welcome, Dr. Saurav. You're most welcome to the webinar series organized by Nasi Delhi chapter. So you are kindly requested to start sharing your screen and start your presentation.
You are mute, Dr. Saurav. You have to switch on your mic.
Yeah.
Yeah, can you hear me?
Yeah, now we can hear you. Welcome, Dr. Saurav. It's a
Welcome,
pleasure
sir.
to have you here after a
Yeah,
long
my
time.
pleasure too.
Thank you so
I
much.
have a bit of problem with the camera. So maybe actually I'm using desktop and this camera is just the phone camera I'm using.
It's not a problem. It's not a problem. As you share
So,
your screen, it's
yeah,
not a problem.
I'm
Please
gonna
go ahead.
share my screen here.
Yes,
Yeah.
please.
It's disabled, I can see. But I'm supposed to be the co-host, right?
No,
You
it's
are a
safer
co-host.
that way.
Yeah, you are a co-host, sir.
But the screen sharing is disabled here.
Just a minute, ma'am.
It's still not shared, no?
Yes, sir. Yeah, you may now please share the screen.
Yeah, now it's active.
Yes.
Okay. Can you see my screen?
Yes,
Yeah,
sir.
yeah.
Yes.
We can see now. We can see now.
Yes, but we can see
Zoom
Zoom on
written.
it.
Yeah.
Yeah,
Yes.
now we can see.
So you have to scroll up, I think.
Yeah. Just hold on. This I'll of course share. Okay. With whatever
Yes, perfect.
development happens today. Basically, this is on relativistic electrodynamics. So I guess most of the things on the classical electromagnetic theory at the undergrads level have been covered by previous speakers who have taught on electromagnetic theory. So I'll give you a preliminary introduction to the to special relativistic electrodynamics. Okay, starting from the review of classical electromagnetism, of course, the emphasis would be on solving problems, okay? But I'll not directly refer to, say, the NET or GATE exam problems. I'll, of course, do some, I'll supply the worksheet and work out certain problems in the worksheet. But the most important thing is that the concept development is necessary because it's a bit of advanced level compared to the BSc level lectures which have been taught on electromagnetism previously in this lecture series.
That's just perfect, Dr. Soor. Your lectures are meant to serve this particular purpose only, because the concepts have to be very well understood. Thank you.
Okay. So these are the lecture notes. The first phase of the lecture notes. This I'll upload, of course. Okay, and this consists of 3 chapters. The first 3 chapters of the notes. These are based on the lectures I have given on the course on electromagnetic theory and electrodynamics, the master's level course for the first year MSc at the Delhi University. And as we go on, in the subsequent lectures, I will append to this. Okay, so more and more chapters will come, specifically the chapters on the problems. Okay, besides, I'll have I'll also upload one worksheet. This is the worksheet. Okay, is there a way to upload right now? Can I upload it right now? This worksheet. There are 4 problems here. Or otherwise, I'll do it at the end. Okay. So I'll start right from the review of classical electromagnetic theory by Maxwell. Okay. So there are preliminary stuff like electrostatics and magnetostatics. I'll skip that. I'll go straight to classical electrodynamics and then to the relativistic phase or the generalization of the classical electrodynamics. So the contents are as follows. You can see. I'll start with the Gauss law and the non-existence of magnetic monopoles, and then the equation of continuity, Ohm's law, Faradays law, and so on. So that will constitute the brief review on Maxwell's theory of classical electrodynamics, and then the confrontation of Maxwell's electromagnetism with then existent Galilean relativity, which led to the formulation of special relativity theory, and then the rigorous stuff on the special relativity theory before plunging on to the relativistic generalization of Maxwell's theory, that is the covariant formulation of Maxwell's equations and the transformation of electromagnetic fields, the motion of charged particles in constant or uniform electric and magnetic fields. So there are all sorts of exercises on that. So let's begin with a brief review of Maxwell's theory of classical electrodynamics. So as you can see, the classical electromagnetic theory, known as classical electromagnetism, that deals with physical phenomena involving interactions of electric charges or currents and the distributions as well within the domain of classical Newtonian physics. That means we will be dealing with electricity and magnetism at length scales which are much higher than the quantum scale or the atomic scale, which is of the order of 10 power 8 to 10 power minus 8 to 10 power minus 6 centimeters. By the way, I'll be using the Gaussian or CGS units all the way through. So if anybody wants to work in SI units or the MKS units, then he or she has to do the appropriate conversion. So classically, what do you mean by the classical physics? We have some inherent assumption of the validity of certain mathematical limiting processes in which the charges and the current distributions. Current means the flow of charges. So charges are everywhere. Whatever theory, not just electrodynamics, consider any theory, we have we're concerned with some kind of charge. For example, in gravitational theory, the charge is called the mass. Okay. And here in the electromagnetic theory, we have the electric charge. We can also have the magnetic charge, but magnetic charge is a bit hypothetical. In classical electrodynamics, there is no scope of any magnetic charge or magnetic monopole. I'll come shortly to that. But bound magnetic charges can exist in some theories. So there is actually the inherent assumption of the validity of certain mathematical limiting processes in which the charge as well as the current distributions could be localized in infinitesimal small volumes of space. So this is the limiting assumption, what is known as the classical limit. In other words, the classical limit assumes that the elementary charge or current loop has a continuous density distribution, and the limiting processes would yield results that agree with the experiments on non-atomic scales. So Maxwell's theory of classical electrodynamics, or Maxwell's electromagnetism, is a generalization and in some sense a unification of the classical static theories of electricity and magnetism, when the electric and magnetic field vectors as well as the sources are allowed to vary with both time and space. The entire formulation is based on certain empirically established results and some idealistic postulates from robust argumentations, which we shall discuss. So the first thing that comes is the Gauss law. So in electrostatics, the Gauss law describes the variation of the static electric field in the way that the total electric charge contained in a given volume is the resultant of electric lines of force entering into or getting out of the volume. As this happens to be the case at every instant of time, one may straightaway postulate that the Gauss law would continue to describe the field variation in space, even in electrodynamics. This is important, okay? So even when the configuration changes with time, we can assume the Gauss law to hold. The reason is that it is a divergence equation. I'll come to this, I'll explain this in detail as we go. So the formal statement of Gauss law in electrodynamics is the following. The net electric flux through a closed surface S is equal to 4 pi times the total net electric charge Q in a volume V, which is enclosed by the surface S. Okay, let's say the surface S has outward pointing unit normal N. So we have this relationship. This is the flux, electric flux, which cuts through the surface S. Okay, and Q is the electric charge, which is contained in a volume that is enclosed by the surface S. Okay. So Q is the total charge enclosed in this volume. So be careful with the notation. normally in textbooks, you'll find notations like this is often written as, this thing is written as ds vector, okay, this whole stuff. And this is written as dv. I'll use d2x and d3x. d2 means it's two-dimensional. So in Cartesian system, d2x is simply dx1 dx2, where x1 and so we have a two-dimensional system, x system with coordinates x1, which we can call x, and x2, which we can call y. So it's xy, okay? And also I'll use superscripts. Don't confuse this with power. This is not power, this is superscript. If I want to write, say, x squared, then that means it is x1 squared. Okay, this is superscript. As we go on, I'll explain we have to distinguish between superscripts and subscripts. I'll be using some abstract notations for the sake of the relativistic electrodynamics we shall do later. So we have this. Now, plugging this 1.1.2, this equation in this, and using the divergence theorem. So I can use the divergence theorem. This is the surface integral. I can convert the surface integral via the divergence theorem to a volume integral. And the right-hand side is this thing. Okay. So what I have done, I have transformed this to a volume integral. And the right-hand side, I have just plugged in the Q here. So this implies that from this, I can just take out this, I can write as d3x and then divergence of E minus 4 pi rho. Okay. Now, this is over a volume V, and this volume V is arbitrary. You can take any volume you like. So this integral operator is arbitrary. So, and this whole thing is 0. So that means this integrand should be equal to 0. And hence, we shall have this equation. This is the Gauss law in the differential form. For the magnetic field B, the corresponding statement can also be written, the Gauss law for magnetism. The net magnetic flux B through a closed surface S would vanish identically if a volume V, which is enclosed by the surface S, consists only of free magnetic charges or monopoles. Okay. But unfortunately, we get this equal to 0. Why is it 0? Because, yeah. So by the same trick, you can convert it to this thing to a volume integral, and the volume integral will give you divergence of V, just as the volume integral gave divergence of E here. Here, the volume integral will turn out to be divergence of B, and the right-hand side is 0. So you'll get divergence of B equal to 0. This physically implies that the effect of the magnetic field lines entering into any elementary volume of space is exactly cancelled by the field lines exiting that volume element at a particular instant of time. Okay. This will not happen at different times, of course. Okay. So divergence of B at a time t equal to t1 is not equal to the divergence of B at time t equal to t2. But at a given time, the divergence of B equal to 0. So this means that magnetic monopoles cannot build up anywhere in space, or we can equivalently state that magnetic monopoles do not exist. Once again, we have to use this with caution, because I can tell you there are systems in which bound magnetic monopoles can exist. Okay. But in classical electrodynamics, the assumption is of limiting mathematical processes. Okay. Mathematical limiting processes. So we should always have a continuum. We cannot discretize the space. So whatever remains integral, it will remain integral. So in that sense, the divergence theorem will always hold, and hence we should have the divergence of B equal to C. The next thing is the equation of continuity, which is basically the charge and current conservation relation. The equation is given in this form, where J is the density of the current, which is due to the flow of charges, and rho is the density of the charge. So this is the relationship, and the interpretation is as follows. If we integrate over a small volume V, then we can see from here, you just take it to the right-hand side, you get a minus sign, and then integrate over a volume V. And this will give you the total charge time derivative. Okay, because this d3x del rho del t, there are two operators. One is the integral operator, and then there is the differential operator. You can always interchange them because they commute. So you can write it like this, and this guy is nothing but the Q. So you have the partial derivative of Q with respect to time, and the right-hand side, so the other side, you have divergence of J. When you integrate over the volume, you can convert the integral to a surface integral where the surface S encloses the volume V. So you have to just integrate this divergence of J over the volume V and convert the integral to a surface integral using the divergence theorem. So you get this relationship, and so you get this relationship. So what it signifies is that this is nothing but the flux of J. So what it states is that the time rate of reduction of charge within a given volume, so time rate of reduction is due to this minus sign, however small, should balance the outward flux of charge through the surface enclosing that volume in order to conserve the total charge. So this is nothing but the statement, the alternative statement. This continuity relationship is nothing but the alternative statement of the conservation of total charge in a given system. For charges with some density rho moving freely with velocity v, the resulting free current density, sometimes called the conduction current density, is often written as J equal to rho times V, and this continuity equation then reduces to this. So these are just the relationships. Some of them are empirical to build up the formal theory of classical electrodynamics from the static theories of electricity and magnetism. So previously, firstly, you take electrostatic theory, where you have only the static electric field, and magnetic field is switched off. And the static electric field means it's not time varying. It's not changing with time. And so are the sources. So the source is, in electrostatics, the source is this charge density, which is independent of time. Okay. In magnetostatics, on the other hand, the source is the current density, which is also independent of time. Okay. But here we are trying to build up a theory in which the sources as well as the fields are varying with space as well as time. So this is the generalization. And as we shall see, this leads to a unification of some sort. Because unification means, what do we actually mean by unification? Unification means there should be some correspondence. Because if we generalize in some way, then generalize some equation in some way, the associated equation will be generalized in a similar way. So that is what we call the unification. And then there is another empirical relationship, that is a purely observational fact is summed up in purely observational fact means it's empirical. It's just noticed from experiments. Is summed up in Ohm's law, which states that for most conductors, a linear relationship holds between the current density J and the applied electric field E that produces it. In particular, the linearity is often represented as a proportionality with the corresponding factor sigma, known as the electric conductivity, being a characteristic of the conductor. But remember, this proportionality is only an approximation. Okay, you may think of this as an expansion. So the J is expanded in powers of the electric field. Okay, Ohm's law is just the linear term in the expansion. So if you Taylor expand the J in powers of E, then you'll have a constant, then E squared plus E cubed, and so on. Okay, the first and the lead term is E. And for perfect conductors, we should have the sigma approaching infinity, whence the electric field, which is J divided by sigma. So sigma approaches unity means the electric field, the applied electric field, is infinite. Sorry, the resulting electric field is infinite. So in other words, a conductor is said to be good, if not perfect, if the electric field required to drive the current in it is negligible. Ohm's law is actually an approximate, as I was telling, but effective realization of the statement that the density J of the current flow due to the motion of charges is proportional to the force per unit charge F in most substances. If the force is electromagnetic, then for small enough velocities of the charges, F is approximately equal to E, the applied electric field, and hence we have the Ohm's law. The next comes Faraday's law, and once again, this is a caution. Faraday's law is again another empirical law, very powerful law. Okay, this inference was drawn by Michael Faraday on the basis of a series of experiments in mid-1850s. And the formal statement is that a changing magnetic flux linked by a closed circuit C causes a transient current flow in the circuit. Actually, the changing magnetic flux induces an electric field E in the circuit C. The line integral of E, or the electromotive force, is induced around C. So this is the line integral of the electric field. So once again, the changing magnetic flux induces an electric field, and this electric field will in turn lead to the so-called electromotive force. The electromotive force causes the flow of transient current in C by virtue of the Ohm's law. And the Faraday's law is formally stated as the induced EMF around any closed circuit is proportional to the time rate of decrease of magnetic flux linking the circuit. Okay. So where from it all stemmed up? Basically, if there is a circuit and there is a current flowing through the circuit, if you bring some charge near to it, then there will be some induced electric field. In other words, if you change some magnetic field, so if you bring a bar magnet close to the circuit, then there will be an electric field induced because of the bar magnet. So the effect is all about induction. And the interesting thing is that it is a decrease nonetheless. And that it is a decrease is specified by Lenz's law, which states that the EMF induced in a closed circuit gives rise to an electric current, which is in such a direction that the magnetic field due to it opposes the change in the magnetic flux that has caused the induction. So in mathematical terms, we can simply write the EMF equal to minus 1 over C dB d phi dt, where phi is the magnetic flux cutting through the surface S. Okay. And B is the magnetic induction in the neighborhood. So from this relationship, we have the relationship, the definition of the electromotive force here and the Faraday's law here. Just put them, you get this relationship. But this is a bit restrictive. This is very restrictive. This relationship holds only when the circuit is static. Okay. So this is the explicit mathematical form of the Faraday's law, which is valid as long as the circuit C is supposed to be held fixed in space. Now, held fixed in space means what? Which space? It's the absolute space. It's the Newtonian absolute space, which had been abolished later on. But that time, the notion of absolute space existed. What if the circuit moves with respect to some frame of reference? Okay, so we are slowly entering into the realm of relativity. So what if the circuit moves with some velocity v, say a constant v, with respect to some coordinate system, or say the laboratory frame of reference, as is usually taken, then the equivalent statement is the same. Only thing is that this motion with fixed velocity v, remember this velocity v is fixed with respect to some laboratory frame, some frame of reference. This is not fixed, or we don't have any notion of an absolute space. Okay. So when we have different frames of reference, one is moving with respect to other with constant speed, then what will happen to the Faraday's law? The observation is that that motion will be taken care of by what is known as the convective derivative. So this total derivative has to be replaced by the partial derivative. I'll in the worksheet I have an exercise, okay, based on this. So this is a well-known problem. This came to the entrance exams of many universities in India and abroad. Okay, MSc entrance, and as well as in some competitive exams. So this thing is very, very crucial. So what we basically have to use is that whenever there is a moving circuit, this total derivative has to be replaced by what is known as the convective derivative. Okay. Now, the question is, what becomes of this convective derivative, this v dot grad term, v dot del term? Okay. I'll explain this via a problem shortly. So this, the thing is that this E is the electric field, this E here is the electric field in the laboratory. And we use the Stokes theorem to convert the line integral, this line integral, to a surface integral over a surface S that is bounded by the circuit C. So I convert this line integral to a surface integral using the Stokes theorem. Okay. As I convert it, this relationship will come out, provided there is certain transmission involved, transmission between the electric field in the moving frame and in the lab frame. E is the electric field, the E here is the electric field in the laboratory. So there should be some relationship between E prime, which is the electric field in the moving frame, and E, which is the electric field in the laboratory frame. As the circuit moves, with respect to some inertial coordinate system, say the laboratory frame of reference, this relationship will dictate how this convective derivative will take care of the motion or of the transformation. So once again, try and understand. You have to generalize this Faraday's law, this restrictive Faraday's law, which holds only for a fixed circuit or static circuit, to the scenario where the circuit moves with respect to a laboratory frame of reference. Let's say E prime is the electric field in the moving circuit, and E is the electric field measured in the laboratory frame. Okay, there should be some transmission relationship between E prime and E, and that should take care of this extra piece in the convective derivative, and hence this total derivative would be converted to the partial derivative. Okay. And after that, using the Stokes theorem, one arrives at this relationship. this surface is arbitrary, so this means the integrand is 0. So we get the differential form of Faraday's law. This is the generic form which would hold for any moving circuit. Okay. Now, it's written here. While working out the mathematical equation for the Faraday's law, in a general case of a charge moving with a fixed velocity v, with respect to the laboratory, one demands that the equation should be form invariant. That is, Faraday's law should be covariant under a frame transformation, under the frame transformations in Galilean relativity. Such a demand implies that one should have the relation between the electric field E prime in the moving circuit and that in the laboratory. So let's say you have a laboratory frame of reference. Yeah, so this is your laboratory frame of reference, and there is this circuit C, which moves with respect to this frame of reference with some fixed velocity v along some direction, let's say. Okay, so an observer moving with this circuit will measure electric field E prime, whereas the observer in the laboratory will measure the induced electric field equal to E. And the relationship between E prime and E should be this, so as to have the Faraday's law in this form. What is the requirement of keeping the Faraday's law in this form? That means you have to have the Faraday's law to be form invariant in under Galilean transformations, Galilean relativity. So in Galilean, you should call a law to be a law when it is invariant under a relativity principle. Otherwise, it cannot be called a law. It would be a hypothesis only, or some conjecture. So it becomes a law only when it remains intact in form under some relativity principle. That means when we go from one frame to another frame, we are basically transforming from one quantity to another quantity, E to E prime. Okay, and similarly, B to B prime. So if this holds in the laboratory, then in the moving frame, one should have this relationship. So that means this equation, the mathematical equation, should be invariant in form. The form of the equation cannot change. Then and only then we can call it a law. So that means this is invariant in form, or what is known as covariant. This is what we mean by covariance. Now, the question is, why is that to be taken in this fashion? Well, I'll not explain this at this stage. I'll do this via some workout example. Now, for a free particle with charge Q at rest in the moving circuit, the force due to the electric field E prime is therefore given by Q times E prime, which is Q times E plus 1 over C V cross D. Are there any questions? Because these are very conceptual stuff. If you have any doubts, you can ask me right away. Okay. Anyway, I'll explain this in more detail when we'll do exercises on this. Now look at this. So this is this is the force due to the electric field E prime. That is the electric field measured by some observer who is moving with the circuit. So say you have a measuring apparatus fixed to the circuit. As the circuit moves, it records the electric field. And you also have a measuring apparatus at the laboratory. So in the laboratory, the electric field E is recorded by that apparatus, whereas the apparatus fixed to the moving circuit records E prime. Now, the force due to the electric field E prime is just the charge times this electric field by definition. So we have this relationship here. Okay, the force written in terms of the laboratory fields. These are the fields measured in the laboratory. So in the laboratory frame, the force due to the corresponding electric field is complemented by a force due to the magnetic field B. So what we have here is the total force. This is the force. You can split this as QE times Q by C V cross B. QE is the force what the laboratory observer will calculate corresponding to the electric field that observer records in the laboratory. Okay. But there is some additional force coming here, which is Q over C V cross B. This is a purely relativistic effect. Okay, this force is a purely relativistic effect. So from the laboratory point of view, this additional force FB can be interpreted as that experienced by a current of density J equal to rho times V due to the motion with velocity V of the free charge Q. Q is nothing but the volume integral over rho, where rho is the charge density. Now, this is a consequence of the postulate that the Ampere's force relationship in magnetostatics, which follows from the BarretSavart law, can be generalized in a straightforward way in electrodynamics. So that for the free charge Q and a fixed velocity V, one has this. So this is nothing but the generalization of the BarretSavart law. What is the BarretSavart law? BarretSavart law is simply 1 over C d3x J cross B. Okay. Do you remember that? It's the it follows from Ampere's law. Okay, I'll come to that in another exercise. Okay. So this is in magnetostatics, when in static magnetism, you just have the force, magnetostatic force. So if static, that is a function of x only. Okay. So this is 1 over C . This is the formal statement of BarretSavart law. It follows from Ampere's law. Once one defines the magnetostatic field from there. Now, the task in electrodynamics, when we are trying to frame a theory from the static theories of electricity and magnetism, what we require to do, we have to require certain relationships. Okay. Is there any distortion in my audio? Or is it?
No, sir, it is okay.
Hello?
You are audible. You are clearly audible.
Yeah, because it's showing here that it is unstable a bit.
Okay, okay, okay. No, that
so
there
I
is no
thought that,
distortion. It is clear, sir.
It's okay. 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 So here, what is being done is that this BarretSavart law is generalized right away. So simply the x are in the argument, when it is time dependent, we just use the same relationship here. This is of course a conjecture, but the conjecture will prove to be correct if that gives you the correct interpretation. So what we find here is that, now, as I said, J is rho times velocity. So we can write it like this. And this velocity is fixed. So we can write it in this way. So this integral acts over rho only. And this is V cross B. Now, be very careful in doing this sort of calculations. And we'll do more and more this sort of calculations as we go on. Be careful with the arguments. The x prime is the location of the source. The x is the location at which the field is calculated. And this integral is over the source volume. Source volume, let's say V prime. So this B can actually come out of the integral. So the integral acts only on the J. And J is rho times V. B will also not participate in the integration. So what will participate ultimately is T3x times x prime times rho x prime. And which is the total charge? This guy is the total charge. So this is total charge divided by C, V cross B. And that's precisely what we are getting here. Okay, what we are getting in this equation. Of course, as one may notice, here we have made allusion only to Galilean covariance of Faraday's law. Strictly speaking, this seems to be an approximation because, as we shall see later, the Galilean principle of relativity is only valid for frame speeds v much, much less than c. Faraday's law is no approximation though. Its velocity, its validity is beyond that of Galilean relativity, and so is the validity of the governing force equation, referred to as the Lorentz force on a particle of charge q moving with a velocity v in an electromagnetic field. So this is the force which keeps this Faraday's law intact even under more general relativistic transformation law, not just to Galilean relativity, even more general relativistic principle. Now, the last thing is the generalization of Ampere's law in magnetostatics. So what we have done so far, let's recap a bit. So what we have done, the task is to generalize, to formulate the equations of electrodynamics from the static equations. So basically, we have electrostatics, electrostatics here. In electrostatics, what we have density function of x only, and there is no current, J is 0. And the electric field, magnetic field, all these are functions of x only. Okay. And what are the relationships we have? We have the Gauss law, which is divergence of E x equal to 4 pi rho x. Okay. Curl of E x equal to 0. In magnetostatics, on the other hand, we have rho equal to 0, and J is a function of x only. No time dependence. It's static. So once again, E, B, these fields are functions of x only. We're doing everything in free space. And the corresponding equations are, one equation is divergence of J x equal to 0. So this is the conservation of the current. Okay, just as the rho is a function of x here, which is the conservation of the charge. So in electrostatics, the conservation of charge is simply d rho dt equal to 0. So rho is a function of x only. But when you consider a vector, then its spatial derivative has to be taken into account as well. The space derivative is given by this operator. Okay, and the space derivative is also 0. So J is independent of time, and the space derivative of J is 0. And what relationships we have? We have the Gauss law of magnetostatics, which is divergence of B equal to 0. And we have the Ampere's law, curl of B equal to 4 pi over C. Now the task is, when we have space and time dependence in electrostatics, we have rho x going to rho function of xt. So is J x going to J xt. And similarly, the fields, electric field, magnetic field. Okay. What by the conservation of charge, we have divergence of J not equal to 0. This is equal to minus the partial time derivative of rho. Now, we have to appropriately generalize these 4 equations, 1, 2, 3, and 4. Okay. The divergence equations, as we have shown, I have pointed out, the divergence equations are generalized straight away. Divergence of E xt is generalized to 4 pi rho xt. And divergence of B xt is still 0. Okay. So the divergence equations, which are scalar equations, divergence means scalar. The right hand side is a scalar quantity. The left hand side is also a scalar quantity. So these are scalar relationships. The scalar relationships can be generalized in a straightforward way. You simply replace x in the argument with xt, and you are through. But what we have seen here is that, for example, this vector equation, curl of E equal to 0, this is no longer true. You cannot generalize it in a straightforward way. This gives you minus 1 over C del del T of E. So that is my Faraday's law. Okay. Now, what happens to this? So this has to be generalized in an appropriate way. One can try first up a straightforward generalization. Just replace the argument in x, argument in b, argument of b, which is x, by xt, and the argument j of j from x to x and t. But that would lead to inconsistency. That would lead to inconsistency. So in magnetostatics, we have had this relationship. And if we try to generalize just by changing the argument from x to tx, what will happen? We can write the equation as curl of bxt equal to 4 pi over c jxt. Okay. Now take the divergence of both sides. So we have curl of bxt equal to 4 pi over c jxt. Take the divergence of both sides. The left-hand side is 0. The right-hand side is 4 pi over c minus. So this is a contradiction. Okay, this is a contradiction, and so what is required? What Maxwell realized that, well, what we have to do, simply merely changing the argument from x to x and t will not do. We also need to change the source, the effective source. That is, we have to change j to some j effective, okay, such that this extra piece which comes after divergence would be taken care of.
रबड़ जलने की बदबू आ रही है ना? तार तो नहीं चल रही कोई इसकी?
Is there some? Can you just turn off your?
बाहर चला रहा है कोई? मत चलाओ.
Who is disturbing? Anyway, so so you have to change the argument, as well as you have to replace. You have to make a generalization of the effective current. which is the effective source. So, and this was the generalization. This was the generalization. So instead of writing, so what we require to do, you have to write curl of B, where B is a function of x and t, is not 4 pi over Cj, but 4 pi over C J effective. Okay. Then take the divergence. Then dive curl of anything is 0. So this will give you 0. Is 4 pi over C divergence of J effective is 0. So this means that you have to define some effective J whose divergence would be 0. This effective J is not the original source which we had here in magnetostatics. So, so this should be divergence of J plus some J extra. Okay. And the left hand side is 0. Divergence of J is minus del rho del t. So this is 4 pi over C. This is 4 pi over C. Sorry. Minus del rho del t plus divergence of J extra. Okay. So that means the divergence of J extra is minus del rho del t, equal to del rho del t, because the left hand side is 0. So this means that divergence of J extra is del rho del t. But del rho is the source current. You cannot use it right away. This is because this extra piece is coming spontaneously because of the field configuration. So you have to convert this, write this in terms of the field. How to write that? Use the Gauss law. So this is del del t, and what is Gauss law? Gauss law is divergence of E equal to 4 pi. So this is 1 over 4 pi divergence of E. Okay. So that means this is, there are two operators, time derivative and space derivative. You can interchange, you can write it. Divergence of divergence of 1 over 4 pi so you identify this extra piece which you require should be equal to 1 over 4 pi del E del T. Okay, this is known as the displacement current. You see, it's precisely 1 over 4 pi del E del T. It comes from here. It's because it's basically a discrepancy, and the discrepancy is being taken care of by this way of generalizing the full equation. In SI units, it's simply written as epsilon naught times E. This thing, okay, where epsilon naught is the electric displacement. Okay, epsilon naught E is the electric displacement, epsilon naught is the free space permittivity. I guess you have already had exercises on electric displacement, parallel plate capacitors, and so on. So I'll not go into those details. This course is mainly oriented to the relativistic generalization. Okay, so only exercises related to these rigorous calculations concerning the relativistic generalization as well as concerning the functional dependence would be considered. Okay, there'll be explicit on-hand exercises on that. So we have the fourth equation, which is given by this, along with the three equations which I had written before. So these four equations, so two divergence equations and two curl equations. In SI units, they are given by this, where mu naught is the permeability of free space, and only thing you have to remember is this relation, which is epsilon naught mu naught equal to 1 over C. What is C? What is C? C is nothing. C is some constant. Okay? Don't make any misconception with the speed of light, because we have not proved that and will not be proving that. What you'll see later on, C is the speed of propagation of electromagnetic waves. Up to that only. We'll just keep up to that interpretation of C. We'll never interpret C as the speed of light, because for that you have to do the Hertz constructions, which I think it's a high-level topic. If anyone is interested, can look into Jackson's book. There's a full chapter on the Hertz construction, okay, which proves that C is indeed the speed of light in free space. It can be proved from some thought experiments, but because of time constraints, I cannot go into those details. In my notes, those chapters will also be there, the full notes, which I'll upload later on. You can see those chapters as well, but I'll not touch upon those chapters. Now, the last thing is the electromagnetic potential. So we have divergence of B equal to 0, and divergence of curl of anything is 0. Curl of any blah blah, this is 0. Any vector. Okay, so we can always identify B as curl of some vector. Okay, this vector is what we call potential. This is the magnetic vector potential, or simply the vector potential. And also we have the Faradays law. We can put that in Faradays law, and so this is so Faradays law is curl of E plus 1 over C del B del T, and B is curl of A, and that is 0. So once again, this operator and this operator could be interchanged. So you can effectively write curl of E plus 1 over C del T of A, which is this. Okay. Once again, you see, you have another vector identity. Curl of gradient of any scalar is 0. Phi is some scalar. So you can identify this whole stuff as some scalar. Okay, as some scalar, which we call minus phi. So this thing is identified with minus phi, where phi is known as the scalar potential. The minus is by convention. The minus is by convention, so as to make it similar to the this um, just as we have in the central force problems. Okay. So this is for that purpose. So we have this full relationship where we have two potentials. One is actually four potentials. One is there are four scalars involved, this phi and the three components of A. Three components of A would give you three scalars, and there is another scalar phi. So there are four scalars. Okay. Actually, it's written a detailed account of potential formulation of electrodynamics will be given later on, but I don't think it could be given in these lectures. I can supply the notes, of course. For the time being, we shall discuss in the next section the conflict that arose between Maxwell's theory and Galilean relativity, but not today. Let's do some workouts, okay, some exercises on this. May I take a 2 minutes break because my throat is. Can I take a couple of minutes break? Just for water. Hello. Hello. Okay. Okay. Just allow me a couple of minutes. Okay. Okay. Thank you. Okay. Thank you. Shall we start now? Okay, let's do some exercises. this is the worksheet. There are 4 problems, which of which I'll try and do as much as I can in the given time. Okay, the first problem is on magnetostatics. Okay, this is the simple this magnetostatic force law, or the Ampere's law, Ampere's circuital law, and you have to express this in this fashion. Okay, the second question is much more involved. That also concerns magnetostatics, but it has 2 parts. One is the formal statement of BarretSavart law. The other one is to prove that is to find the relationship, find the curl of this B. Okay, which I can tell you, it's a longhand exercise. It's not easy. But excerpts from this have come in many university examinations. Okay, parts of this, the techniques you learn will be useful for you. The third problem I will not do. This is a problem that would be left for you. If you should, of course, try this problem at home. If you require some hint or anything, I can give that at the end in my last lecture. So I'll give a series of 10 lectures. In the last lecture, I'll give the hint of how to solve this, okay, and possibly provide the solution. But for the time being, you should try. The fourth problem is on Faraday's law. This is a very crucial problem. This has appeared at many places, even in the big universities like Princeton, MIT, and many others. And I have supplied the useful vector identities and other relationships. You have to only use the vector identities as well as the definition of delta function and its identities. Okay. Wait a minute. Drawbacks of classical electrodynamics. Yes, drawbacks of classical electrodynamics I will not touch upon today. There is a full chapter devoted to that, and that will be taught day after tomorrow. Okay, which is the second chapter in the lecture notes. You can go through the lecture notes if you like, but for the time being today, I'll not touch upon that, the drawbacks of Maxwell's electrodynamics. The main drawback is, of course, the conflict with main or you can say the only drawback was that of its conflict with then existent relativity principle, which was the Newtonian or Galilean relativity. So it's up to you whether I should you should try this. You want to try these problems now. I mean, you take time or try the problems yourself, or shall I work out a couple of problems today, or I switch over to the next chapter? So I want the opinion. If you want, if you require, if you want to try yourself, you are welcome. You are most welcome. Okay. In any case, I will work out some of these exercises in these lectures. But if you want to try yourself first up, you are most welcome. Then I can switch over to the next topic. You just give me your opinion. Okay, so the general consensus is that you want to try first. Okay, fine. Absolutely. That's the spirit. That's what it should be. Because now there are many things which have come, and this is the same old electrodynamics, but in a different sort of dress up. So it's better you should try first. In any case, I'll do in the first lecture of day after tomorrow. Okay, but you should try. Yeah, that so I can go on to the next topic. I can go on to the next topic, which is the conflict with Maxwell's electromagnetism with Galilean relativity. So first, let's digress the Galilean transformations. You have two systems of, let's say we have two systems of reference, sigma and sigma prime. Don't confuse this with the summation. This is sigma, just a symbol. Okay. Unfortunately, I should have used the S. Anyway, sigma is characterized by coordinates xi. I'll use this notation. You have to try and get acquainted with this notation. X superscript I. These are the coordinates. This is the index notation. This means that we have a 3-coordinate system, x1, x2, x3, or x1 is x, x2 is y, x3 is z. Later on, we'll use x1, x2, x3 also. But x1 is different from x superscript 1, remember. X2 is different from x superscript 2. So the superscripts and subscripts, they have to be distinguished. Okay, the superscripts are the usual coordinates. The subscripts are called the co-coordinates or co-system coordinates, which I'll explain later on. So Galilean transformations, Galilean relativity is basically Newtonian relativity, where the time is some parameter. It's not treated as a variable. It's a parameter in the system. Okay. The coordinates are just the space coordinates we have, x, y, z. Now we have two such coordinate systems or reference frames. One is the unprimed system with coordinates x1, x2, x3, and another one is the primed system with coordinates x prime 1, x prime 2, x prime 3, and time t prime. And let's say the origins of these two coordinate systems coincide at time t equal to t prime equal to 0. So this is a simplification we are making here. Of course, this will not hamper anything, any physical understanding. And sigma prime is moving relative to sigma with constant velocity v in an arbitrary direction. And for simplicity, we choose the axis of the two frames to be parallelly oriented. Okay. This is x prime. Don't bother about the left-handed, right-handed system for the time being. The Galilean transformations equations are simple enough, you know that, which are this. And the principle of Galilean relativity says that all laws of mechanics are invariant under the transformations, these transformations. So, illustrate this. Consider a system of particles interacting via two-body central potentials. In the reference frame, The primed frame, the equation of motion of the ith particle of mass I, mi, interacting with the jth particle of via a potential Vij is given by this. This is the well-known relationship. It's a central force problem. The separation between, so there are a system of particles. There are many particles. Let's say this is the ith particle, and this one is the jth particle. And they are interacting via a two-body potential Vij. This is actually the matrix element of the full potential V. The full potential of the system is a matrix. The elements of the matrix are these Vij's. Okay. Now, the equation of motion of the ith particle, which is under the influence of the jth particle and all possible j particles. Okay, so this is from this is the sum over j, where j is not equal to I. Is this? This is mass times acceleration, and this is the gradient of the force due to this potential. And this v is the velocity of the ith particle in the reference frame sigma prime. Okay, in the reference frame sigma prime. So you have to be careful with using the operators. So the time derivative is d dt prime, and the space derivative is d dx prime, which is this. Now, from the first equation, that is the Galilean transformations, you have to simply replace x prime with x minus v times t, and t prime with t. So x prime I minus x prime j is xi minus xj. And so that v prime is dx prime dt prime, which is dxi dt minus v. And that is dxi dt is vi by definition. Okay. And v is the relative velocity between the two frames. So once again, don't confuse with the capital Ij's with the small ij's here. The small I here. The small I means coordinates. Okay. The capital I indicates the particle. In a system of particles, which particle? The ith particle. So it is the particle level. Okay. Ij's are particle levels. These are particle levels. Whereas small I, small j, blah, blah, they are the coordinate levels. Now, we have to work out the relationships between the coordinate differentials in the two frames. So, the relationship between the time derivatives and space derivatives in the two frames, because we are doing a relativistic calculation. So consider, for simplicity, a scalar function, psi. The scalar in the coordinate system sigma, the unprimed system, psi is a function of t and x. Whereas in the primed system, psi is a function of t prime and x prime. And then we can simply write d psi as del psi del t dt plus d psi del x1 dx1 del psi del x2 dx2 and so on. Similarly, in the other frame, it is del psi del t prime dt prime, then del psi del x prime 1 dx prime 1 and so on. Okay. Now, what we require to do, dt prime is equal to dt, because t prime is equal to t. That is the transformation. That is the transformation we have. but x prime is x minus vt. Okay, so in the sum, you have x prime I should be you can keep the x prime I here, but the dxi here is dx prime I is dxi minus vi times dt by the transformational relationship. So you have to equate the coefficients of dt and dxi for each I on both sides. Equating the coefficients, what you get is that the space derivative, if you break it, forget about this. We are considering one time and one space. Okay, for simplicity. So this is del psi del t dt plus del psi del x dx. So for simplicity, just consider one space code. And similarly, del psi del t prime dt prime plus del psi del x prime dx prime. And this I have written as del psi del t dt plus del psi del x prime, and dx prime I have written as dx minus v dt. Okay. Now I'm equating the coefficients of dt and dx from both sides. So see the dx coefficient. Dx coefficient is del psi del x. So equating the dx coefficient, I have del psi del x equal to, on the right hand side, del psi del x prime. Now equate the dt coefficients from both sides. That will give you del psi del t is del psi del t prime. So t and t prime are the same, minus phi del psi del x prime. So in 3 dimensions, this space derivative will become this del operator. So this will generalize to del del t. So the first relationship would be the two gradients would be same, and the second relationship would be the time derivative would be the time derivative in the other frame minus this v dot del prime or v dot del, because these two are same. So inverting, I have this. Okay. Now put this back in the equation we had. This equation. Now I have to convert dv prime dt prime in terms of dv dt, and so as to this del prime to del, and xi prime minus xj prime to xi minus xj by utilizing these relationships. You just do that, you get the same equation. So that this means that this is a law, the central, because this whole thing is invariant in form. The full mathematical equation is not changing its form, although the variables in it are changing, but the form of the equation remains. That is what we mean by covariance. Okay. Now see, now consider a counter example. So this is a purely kinematical illustration. Now consider a kinetic illustration. Kinetic means something related to energy, not motion. Kinematic means something related to motion, and kinetic means something related to energy. So consider a scalar field psi, and suppose that it satisfies the homogeneous wave equation. This is the well-known wave equation. Everybody knows this is the equation of a plane wave. Why plane? That I'll explain. But this is the equation of a plane wave with speed u. U is the speed of propagation of the plane wave. Under the Galilean transformation, what you have is that this del, so you have the relationship, you see, this is the relationship. You have to convert to the primed frame. Okay. So del is equal to del prime, so there is no problem. But what about this? So the second term poses no problem. But the first term, there are two time derivatives involved. And when you break that up, you get this is nothing but del del t and another del del t. Each del del t is del del t prime minus v dot, and then you have to square it. Okay, so that will give you two terms, one cross term and one quadratic term. And what is the physical meaning of v dot del? V dot del is an operator. It has no physical meaning. Physical meaning will come later when I'll explain the physics. I mean, an operator cannot have any physical meaning. An equation can. This equation has a physical meaning. This operator doesn't have any physical meaning. This operator is a tool which is used. Okay. But the important thing is that whether this operator, when you have this extra term in extra operator coming in, whether that operator preserves the physical equation or not. The physical equation is this equation. The physics is encoded is governed by this equation. This gives you the trajectory of particles. What is the physics? The physics is that it's an equation in the configuration space, not in the space. In the configuration space, what people do? People work out the trajectories. That is, solving this equation. This is a second order differential equation, right? Second order differential equation in terms of some interaction, in presence of some interaction. Second order, why second order? Because v is itself a derivative. So it's a second order differential equation. Given some initial conditions, one has to solve this equation to find the trajectory, that is xi as a function of time. That is the solution. Okay. Then you'll get, once you get the trajectory, you know all the physics of it or the dynamics of it. Okay. So the main point is that the equation which gives you the trajectory is the equation which is the mathematical equation representing the physical law. Now, you have made a frame transformation. Whether that mathematical equation is intact or not, that is the question. Whether that frame transformation, this frame transformation, whether it preserves the physical law or not. So the quantity, the operator which you are getting, this v dot del, that is not a big deal. The big deal is that even when you get this operator, whether your final equation is preserved or not. Okay. In this case, it is preserved. In the other case, it is not. And wave equations are so vital equations. For example, the Schrödinger equation, that is also a second order differential, second order wave equation. And that will also not be preserved. Okay. So there are some extra terms appearing in this expression. Okay. So the above counter illustration is an indication that the Galilean relativity is in general conflicting with the electromagnetic theory formulated by Maxwell. To see this, we first show that the scalar psi in this equation, where is that? Here. In the equation 11, this scalar psi could be identified with any components of the electric field vector or the magnetic field vector, which satisfies the Maxwell's equations in empty space. So consider free Maxwell's equations, rho equal to 0 equal to j. So no sources, the free Maxwell's equations. If you take the curl of this equation and use the vector identity here, then from this you get this relationship. This is straightforward. Okay. So only thing you have to do here, you have curl B. Now in this curl B, you use this equation. You use this equation, then a second time derivative will come. And a time space derivative will come. Sorry, a second time derivative will come. So this curl B you have to replace with minus 1 by C del E del T. Okay, so this becomes 1 over C square right? And just transpose this. This is 0. This is 0. So you basically have you just transposing 1 over c square del 2 del t square plus there is a minus. Yeah. This is plus. So you have you will land up to this equation. Similarly, you take the curl of B and use the other equations, you will get this equation. So each component of E and B, so they will satisfy an equation of this pattern. Okay, where your psi is any component of E or B. And this is same as the wave equation before, with the speed of propagation U replaced by C. Okay. And this is regarded as the homogeneous wave equation for the following reason. You assume a wave solution of this form, where K is a constant vector and omega and psi 0 are also constants. Then you can work out the gradient, the Laplacian, as well as the time derivatives, first and second. Putting all these things, you land up to this equation. Okay. And which would be 0 only under the stipulation that this guy is equal to this guy. So the solution thus represents a wave traveling along or opposite to this vector K, known as the wave vector, in the sense that the point of constant phase K dot x minus omega t moves in the direction of plus minus K with speed c, which is determined by this. So you have the wave. If you put a constant phase, this whole thing is constant. What will happen then? If this whole thing is constant, you can simply take the time derivative, you'll get this. And then using this condition, you have c equal to plus minus omega by k. So this is what is known as the dispersion relation. Okay. And since the surface of constant phase, you see, this is a linear relationship. This is linear in x and linear in time. So that means it is the equation of a plane. And hence it is known as a plane wave. Or you can say this is the equation of the wave front. The wave front represents a plane. And hence this wave is a plane wave. Now, how much time I am? 2.5 minutes. Okay. Now, the non-covariance of the wave equation under the Galilean transformation. So, what we have seen? We have seen that equations of this sort, okay, equation of this sort is not invariant under Galilean transformation. Okay, because as we have seen, there are extra terms arising. These are the extra terms which arise. So this is not conserved, not preserved. So if there is, this is a statement of a law, then that law is not valid. Okay, if you believe in Galilean transformations, then at least the Galilean transformations do not preserve that law. Okay, so that is the problem. Now, what we see is that this is problematic for Maxwell's electromagnetism, unlike, for instance, the theory of acoustics. The acoustics or the sound waves are due to compressions and rarefactions of a given medium, for example, air. And the reference frame in which sigma in which the wave equation has its usual form. Usual form means the form which we had written before. That is this form, del 2 del t square, whatever, t square minus this psi equal to 0. This form, in the other frame, this form is not preserved. Okay. So the frame in which this form, the usual form of the wave equation is preserved, is obviously a preferred frame of reference. What is that preferred frame of reference? The frame at which the medium is at rest. Okay, there is no motion of the medium, and hence there is no question of any Galilean transformation. In all other reference frames in which the medium is moving, the direct influence of such motion on the propagation of sound due to the mechanical vibrations described by Newtonian mechanics can account for the extra terms that modify the usual wave equation under Galilean transformations. Okay, the usual wave equation under Galilean transformations. You mark this point because sound waves are what? Sound waves are due to mechanical vibrations. So whatever extra terms you are getting because of a mechanical thing, okay, a principle of relativity which preserves the laws of mechanics, that means that these extra terms would be taken care of by appropriately choosing the medium speed, the speed of the medium. Okay. For the electromagnetic waves, however, the situation is in general different because there is no influence of any intervening medium on the electromagnetic wave propagation other than just supporting the latter. That means supporting the wave propagation. So here, in the case of electromagnetic waves, the intervening medium only supports the motion, but it does not change the wave equation itself. The Maxwell's equations, which govern the electromagnetic wave propagation, involve this parameter C, which, according to Maxwell's theory, should remain fixed in all frames of reference and could be interpreted as the fixed speed of propagation of electromagnetic waves. It is the presence of this fixed C which prevents any possible way to compensate for the non-preservation of the Maxwell's equations and consequently the wave equation under the Galilean transformation. All this stems out the conflict of Maxwell's theory with Galilean relativity. All is encoded in this fixed C. This is the problem. Maxwell's theory thus seems to be incompatible with Galilean relativity. So what are the way outs? Well, three possibilities. Maxwell's theory is incorrect, and a proper theory of electromagnetism must have its equations invariant under Galilean transformations. The second thing is that Galilean relativity applies to the laws of Newtonian mechanics, and Maxwell's theory is correct but bizarre in the sense that the electromagnetic wave propagation always requires a preferred frame, the one in which the intervening medium, the so-called luminiferous ether, is at rest. Okay, so there is supposedly, or it has been conjectured that there is some intervening medium, the ether, and the usual wave equation is satisfied only when only with respect to only in a frame which is not moving with respect to the ether. And the third possibility is that there should exist a relativity principle other than the Galilean one for the laws of mechanics as well as the equations of electronics. Now, the first alternative could hardly be considered viable given the immense success of Maxwell's theory we have had otherwise. The no-go establishment of the ether hypothesis following the works of Michelson and Morley had ruled out the second alternative as well. Therefore, it had all come down to postulating a new relativity principle and asserting a set of desirably linear transformation relations, which, among other things, would keep the form of Maxwell's equations intact with the same speed parameter in all frames of reference in uniform relative motion. That means inertial frames. And the first step towards obtaining such transformation relations and hence to formulate a new theory of relativity is to abolish the Newtonian concept of absolute space and to keep the time and space in equal footing. That is to say, one should now invoke the concept of space-time instead of treating space and time separately, represented by all spatial coordinates, as well as time multiplied by a constant speed from dimensional arguments. So if you say time is a coordinate, then time has to be measured in centimeters, right? And time is indeed measured in centimeters. That unit system is called natural unit system. Time is measured in centimeters. So there is, it is multiplied by some universal constant velocity or speed. At that constant speed is the speed c of propagation of electromagnetic waves. Okay. So such a speed parameter must be a universal constant, which is argued to be the speed c of electromagnetic signals in empty space. I think we should stop here before plunging into the rigorous stuff like special relativity in the next lecture. But first, in the next lecture, at the beginning, I'll do the workouts, or at least a part thereof, and then begin with this the next chapter, which is special relativity. The chapters that would follow are the principles of special relativity. I urge you to learn a bit of tensor analysis, although there won't be much time to illustrate. And then the special relativistic particle dynamics and the covariant formulation of Maxwell's equations. So those are the following chapters. Okay, and the exercises that come.
Dr. Divya,
Yes, ma'am.
are there any questions on YouTube?
Ma'am, no questions on YouTube. There is one question, sir. The students are asking to send the problem sheet.
How can I send that?
You just share it with me, Dr. Saurav. I will share it with them. I'm in touch with each and every student who is attending these classes, either through WhatsApp or through email. So it's not a problem.
Okay,
We regularly.
I can answer the second question.
Yes, sir. Yes.
I have there. I can answer the second question.
Yes.
These are the lecture notes, and one has asked about the references. Well, the references are there at the end of these notes. The bibliography I have put in. Let me show. The last page is the bibliography. Okay, these are the books. The basic book I'll follow is Jackson, only Jackson. I'll not follow Griffiths too much because the Griffiths are weird notations. And I'll follow this reference and to some extent this reference. This is publicly available. Okay, Poisson's lecture notes. And this is Weinberg's book on the relativity aspect, Weinberg's book, as well as Gene Werner's book. These are the main books I'll follow. But above all, I think the lecture notes are self-sufficient. So, and the steps have been rigorously worked out. You can see some of the workouts here, although I don't think there'll be time to cover all these things. Okay, so.
Thank you so much, Dr. Saurav. I think these are self-explanatory types of lecture notes, and you have recommended the best of the books, and they are written right at the end, and they already know some of the books, and now they have to come up to the level of Jackson, as you said. So that is just appropriate. And in the coming few days of your lecture series, I'm sure these things will become much clearer to them. So thank you so much, students. The feedback link is on the chat box. Please fill it up or copy it into your own browser. Thank you very much, Dr. Sur. We have tomorrow.
You are most welcome.
Tomorrow we have molecular physics, and then once again day after tomorrow we have 3 more days of continuous lectures with you. And I'm sure these are more than sufficient for anybody to be oriented towards completing an EMT course as a good revision for any kind of studies, whether during MSc or after MSc.
Just one thing, how can I upload these loads, these lecture notes as well as the worksheet?
You have to just send it to me on email. I'll do it.
Okay, okay, that I'll do. I'll upload the first 2 chapters. As we go on, I'll append to that. Okay.
Yeah.
And I'll also upload the worksheet.
Yes. On the email, if you give it to me, I shall pass it on to them. No problem.
Oh, sure. I'll do.
Okay, thank you. It's a great pleasure for us, and I'm really grateful that you agreed,
Thank you,
because I was
sir.
really bothered that EMT level at the graduation level is over. But what about the post-graduation level? That too has to be covered, and you kindly agreed. So I'm definitely very, very grateful.
So it's my pleasure, because I love this course. I have taught this
Yes.
for 8 consecutive years.
Oh my God. Oh my God.
Yeah.
Yes,
And
yes,
Yeah,
sir,
yes.
but
sir, to mention this, I have been taught by you. So I was
So
there
you were
in,
a student
is
at
that so?
DU.
yes. So
Okay.
I was
Okay.
in the batch of 2014. So, and
Okay.
I had written all the notes that you used to give in the class. So I could
Okay.
recognize
That's great.
these things.
The pleasure of writing while a teacher is teaching is really something that is worth experiencing.
Yes,
During
sir.
my masters, I used to be one person who used to write, comma, full stop, semicolon, everything as the teacher said. We used to write in detail. Years later, they helped me immensely for understanding physics. Sometimes when you are a student, you don't understand those things, but sometime later it becomes clear and so on. So there is
Yes.
definitely a
I
pleasure.
agree. I
Yeah,
agree,
which the
ma'am.
present generation is not now, not that much. They still can do many things by digital means. We had no digital means at that time.
And sir,
We had to write
I
everything.
I used to attend every class, and at the end of the semester I had notes, everything, and uh, frankly speaking, I did not refer any books.
So that
And
means
I passed the exam with good marks.
good. So that's a lesson to be learned for sure.
Yes,
And I remember, Dr. Saurav, the time when there was no Xerox machines freely available to the students, and the
yes.
book was given by the
Just
library.
one request. Just one request. Can you just call me Saurabh? That will
Okay,
do.
okay, okay.
I mean,
Okay, no problem. So sort of those
okay.
days when the books were
Yeah.
lent to you
Yeah.
only for 2 days by the library, and they had to go back. The pressure of completing a particular